Okay. In section 7.3, we're going to discuss confidence interval for sigma. Remind me what sigma represents.
Population standard deviation.
Yeah, well done. Population standard deviation. Now, in creating a confidence interval for our population standard deviation, we're going to need a new distribution. It's going to be this one. It's not called chi, it's called chi. So it's a chi-square distribution. So what's going on with the chi-square distribution? Well, I sent you a link, and I'll pull that up over here. Here's your chi-square distribution. And wow, what can you see about this that's different? All right, tell you what, I'll start out with the similarities. The total area underneath this curve. Any guesses? What was it under T and Z?
1.
Total area is 1. That's where the similarities stop. It's going to start at 0, so it's not symmetric. It changes with degrees of freedom. And there's probably a couple other things I could say about this, but those are the big ones that you should get. Now, with the link I sent you, you can kind of play around with this and move it around a little bit, see what it looks like. So for 1 and 2 degrees of freedom, it looks really, really steep and it looks kind of funky. And then at 3, it does smooth out a little bit. And the interesting thing is, what does this distribution look like if I get up to degrees of freedom like 9 or 10 or 11? What's that starting to look like?
Normal. It starts to look like a normal one.
Exactly. It starts to look like a normal one. Now, that's not something that we're really going to use in this class, but you know, it does start to look like a normal distribution. Now, to build a confidence interval for these things is, you know, kind of a pain. Now, if we were doing this by hand, you would need to figure out chi-square sub r and chi-square sub l. And what those are points in the chi-square distribution that have, you know, a certain percentage of the area in the tails. So chi-square distribution is going to look like that. Chi-square sub r and chi-square sub l are going to be points that have just a little bit of the area in these tails. And the good thing for us is that we don't have to look those up. We don't have to do any calculations at all. We're going to let some software handle it for us. What we're going to need are 2 things. We're going to need the sample standard deviation and the number of sample values, how many were in our population. Now, what's different about this as opposed to the distributions that we look with, or excuse me, the confidence intervals we dealt with earlier in this chapter, is that this is not a nice symmetric interval. I can't just do, for instance, S plus or minus E. That's not how this works. Your confidence interval is not going to be nice and symmetric like it was for the previous couple distributions. That's okay. It's not really going to be something that bothers us. The one thing that I want to highlight here, though, is that in order to create these confidence intervals, the population must have a normal distribution. This requirement is much stricter than in previous sections. In the previous sections, you know, I did say some stuff about it, but here it's really important because the chi-square distribution is very sensitive to departures from normality. So it's something you do have to worry about. Now, we're not going to be checking it like every problem just because I won't be able to get through any material. But do know that this is a strict requirement. And if it's not met, you have to do something else. Probably a non-parametric method, which I'll cover at the end of the course. So let's look at this one, the Atkins weight loss program. In a test of weight loss programs, 40 adults used the Atkins weight loss program. After 12 months, their mean weight loss was found to be 2.1 pounds with a standard deviation of 4.8 pounds. Construct a 90% confidence interval estimate of the standard deviation of the weight loss for all such subjects. So, all right. We'll call this one example A. The information that I need here is going to be N, S, and 90% confidence. So N is going to be 40. S is going to be 2.1. Now, do I really need the mean here? Do I need X bar?
Wait, I thought the standard deviation was 4.8.
Oh, I'm sorry. You're right. I did
Okay.
copy down the wrong thing. My bad. Yeah, I was scanning it too quickly. Yeah, so 4.8. So 4.8. There we go. Had it all the time. Thank you. Let's see if we can't create a confidence interval for the population standard deviation. Where do you think I should go to create that confidence interval?
StatDisk.
StatDisk, yes. Let's go to StatDisk, and then where? I got some stuff left over from last time, but that's okay.
Confidence interval.
Analysis, confidence intervals.
Standard deviation, one sample.
Nice. Standard deviation, one sample. Now, if you have data, you can use that. We've got summary statistics. First thing I have to do is I have to change that to a 90% confidence interval. Sample size was 40, and the sample standard deviation was 4.8, not 2.1. Thank you. There you go. Our confidence interval is between between 4.06 and 5.91. Now there's something below. I've actually got two confidence intervals. What do you think the second one is?
The variance.
Yeah, that's the confidence interval for the variance. How do you go from the standard deviation to the variance? Do you remember?
Square
root.
Yeah, square or square root, depending on which direction you're going. If you're going from standard deviation to variance, you can square this. And you can kind of see that, right? If you square 4 something, you're going to get 16 something. So, okay, nice. Let's state that conclusion in words. I'll do that one for us. We can be 90% confident, and confident, help if I could spell. Confident that the true standard deviation of weight loss is between 4.06 and 5.91 pounds. Beautiful. Now, there was a follow-up question to this, and it was, does this confidence interval tell us anything about the effectiveness of the diet? What do you think? Carly, does this confidence interval tell us anything about the effectiveness of the diet? Confidence interval.
I'm not sure.
Well, the standard deviation talks about the spread of the data, right? Talks about the variation in the data.
Yeah.
But wouldn't we want to know something about the mean of the data, the average weight loss?
Probably, yeah.
Yeah, so this confidence interval really doesn't tell us much about the effectiveness of the diet. It's just how much variability there is in the weight loss. So, okay, you know, there's a fair amount of variability. I mean, not too much, but you know, some. But what I'd be judging him on more is this number right here, 2.1, which was the average weight loss after 12 months. Okay, any other questions or comments on example A? Let's knock off a couple more here.
Wait, I'm sorry. What is the effectiveness of the diet?
It doesn't really tell us anything about the effectiveness of the diet. We don't want to know how spread out their values were. We want to know what their average was. Are they losing weight? Because the spread of the data could include losing weight and gaining weight, right? So people can do either during this 12-month period, and how spread out those values are doesn't tell us if they're losing weight or gaining weight, because they're all going to be part of the standard deviation. But what tells us how they're doing is their average weight loss. So we'd probably want to construct a confidence interval for that to figure out, you know, is this effective? In fact, tell you what, I think we got enough information, we can do this. Let's just do it real quick here. So I'll go to analysis, confidence intervals, mean one sample, and you know, I'll stick with a 95%, even though the data or the original problem did 90%. The sample mean was 2.1. Sample standard deviation was 4.8. So your confidence interval was between 0.5 pound and 3.6 pounds. So that tells me more about what to expect. Now, here's probably a good example of statistical significance versus practical significance. There's a statistically significant weight loss here. You have lost weight on average in this diet. But is it practical? Would you be happy to be on a diet for 12 months and lose at most a bit over 3.5 pounds?
No.
No. I mean, literally speaking, if you eat a really salty dinner, you'll probably put on about 3 pounds worth of water weight. So losing that in 12 months is not very effective. So statistically significant, yes. Practically significant, no. But that would be my measure of whether or not this is effective or not. All right, hope that answers your question, Megan.
Yes, thank you.
Good. Let's continue with the next one. I want to get in 2 more here. Listed below are waiting times in customers in Jefferson Valley Bank. Construct a 95% confidence interval for the population standard deviation, sigma. Now, I'm not going to do all of this. Well, let's see. Let me take a look at problem number 18. Let's see. Okay, so you know what? Maybe we'll do an extended version of this instead. So let's put in the data into our data set, the status. So let me just copy this down here real quick.
We're doing 16A, right?
Yeah, we're gonna do A and B and then compare them. A. So I'm just writing down the data here for myself: 1.2, 5.4, 5.8, 6.2, 6.7, 7.7. Okay, so let me copy this data into our data set, into StatDisk. So go up to StatDisk. Oh. I clear out my old data set here. And let's type in column 1, 6.5. Come on, give me. There we go. 6.5, 6.6, 6.7, 6.8, 7.1, 7.3, 7.4, and 7.7 3 times. So 7.7 once, 7.7 twice, 7.7 3 times. So you should have 10 values in there. Then for the next data set, 4.2, 5.4, 5.8, 6.7, 7.7 once, 7.7 twice, 8.5, 9.3, and 10. Whoops, I must have missed something someplace. Darn it. Let me look back here. 4.2, 5.8, 6.2, 7.
I think you're missing 6.2.
Okay, thank you. Yep, missing 6.2. Now, while you're typing that in, I'm just going to do kind of a little putzing around with some exploratory data. If I remember this data set correctly, the mean was the same for both of these. So 7.15 for column 1. Let's try column 2. 7.15 again. So the mean was the same for both of these. So on average, these are customer wait times in 2 different banks. On average, you're waiting the same amount of time. But is that the only consideration here? Well, what they want you to do is they want you to create a confidence interval for both of these. And we'll start with the first bank, where you have a single line that feeds 3 different teller windows. Compare that to standing behind, somebody who's waiting for the next teller. So that's the difference here. So we'll go to analysis, confidence intervals, standard deviation 1 sample. I want to use data. I'll select my first column. And evaluate. So for bank A, our confidence interval is between 0.33 and 0.87. Now let's repeat this for column 2. And here our confidence interval is between 1.25 and 3.33. So graphically speaking, here's what that looks like. So for Bank A was, the standard deviation of wait times is somewhere in here. For Bank B, it was somewhere here. Are these significantly different?
Yes.
Yeah, because they don't overlap. So there's a statistically significant difference. Now, I'll finish this up. Part C is asking you about the difference between these two. Yes, there's a statistically significant difference. I would want, as a manager, I'd want something like this, because you're giving your customers a more consistent experience. If you look at this, Bank B, I mean, you could wait between 4 minutes and 10 minutes. Boy, if you're out here and you're watching somebody get through in 4 minutes, I know as a customer, I'd be really unhappy. All right. So here you're giving people a consistent experience. Here, there's a lot more variability. So you want to pay attention to that. Okay. Any thoughts or questions on this one? I got to end things here. So the homework section 7.3 should be out there, and there should only be one assignment out there. So work on that and enjoy your weekend. See you.